Okay, so looking at for the material for week 9 of the course here, we're talking about confidence intervals. And this builds very heavily off of that sampling distribution that we talked about last week. If you recall, that sampling distribution, we were taking that normally, either one of two things, either we had a normally distributed population, or we were taking an adequately large enough sample so that we didn't have to worry about the population. But either way, what we were doing is we were taking all possible samples. So let's say our sample size is 40. So we're going to take all possible samples of size 40. From our population. And once we've taken all of those samples, now there's going to be a lot of those samples, what we're doing is we're finding the mean of each sample. And what the sampling distribution is, and sometimes it's called the sampling distribution of the sample means, that sampling distribution is looking at those means of each of those samples. And it is plotting that curve. So let's say the population, the individual values in the population, fall on a bell curve like this, normally distributed, like that. It has the mean for the individual values somewhere in the middle, and of course there's a standard deviation. Well, the sampling distribution of those sample means, in other words, the curve for those sample means, is going to look similar to that, only it's going to be much narrower. You'll notice the center is at exactly the same spot. The population mean, well, actually, let's word it this way. The mean of the sample means is just equal to the population mean. And that is for the individual values in the population. So we take all of these samples and find their means, and then we find the mean of the means, the mean of all those means. The mean of all those means should equal the population mean of each of the individual values, of all the individual values. And then, of course, the width of that is narrower. The width of that, which is called the standard deviation, of the sample means, sometimes referred to as the standard error of the means, that's a very common term depending on what textbook you're looking into, is equal to the population standard deviation divided by the square root of the sample size, where n is that sample size. So in this case, if we're doing sample sizes of 40, that would be divided by the square root of 40. So the larger the sample is, the less variation there is in those sample means. So the narrower that curve is. So the larger the sample size is, the smaller this standard error or standard deviation of the sample means is. So we're now looking at that in light of these confidence intervals. So let's look at some of our basics here. What we're going to look at here in this first section of week 9, chapter 7, is we're looking at interpreting what confidence intervals are and what they mean. We're looking at confidence intervals for the mean of a population. When we know the standard deviation, we'll be looking at when we don't know the standard deviation later on. Looking at critical values, this is part of that normal distribution again. We'll talk about that, working with an inverse normal. Describe the relationship between confidence level and margin of error. So we'll talk about The margin of error describes how wide that confidence interval is going to have to be, how large it's going to be. Find the sample size necessary. So that's a calculation that your calculator does not do for you. So we'll go over that quite a bit, looking at how do we calculate that by hand? How do we use that formula? And then finally, distinguish between confidence and probability. So there's a little bit of a difference there that's often misinterpreted. So let's look at constructing a confidence interval and then interpreting it for the population mean. So we're trying to estimate the population mean. Now, the one thing we're going to talk about here is we're going to talk about the difference between a point estimate and an interval estimate. In a point estimate, we just take a sample, find its mean, and we say, hey, the population mean, well, I'll just use the proper terminology here. Proper terminology is the population mean is, of course, mu, is going to be approximately equal to that sample mean, which is x bar. So we take that sample, we find its mean and say, hey, if we took a good sample, the population mean should be close to this. And that's true. If that's a good sample, it's a representative sample, the mean of that sample should be really close to the population mean. In interval estimate, we're going to use what we know about the sampling distribution, and we're going to construct an interval. Rather than saying it's approximately equal to that number, we're going to say that the sample mean should be between these two numbers, A and B. And we'll look at how do we find those numbers A and B as we go along here. So consider the following example. Simple random sample of 100 fourth graders, so that's n equals 100, is selected to take part in a new experimental approach to teaching reading. At the end of the program, the students are given a standardized reading test. On the basis of past results, it is known that the scores on this test have a population standard deviation, sigma equals 15. Now that's important. We know the population standard deviation. As we get into our interval estimation, that's going to be very important to know that. So the sample mean score for the 100 students was 67.3. So now we're looking at a point estimate here. The administrators want to estimate that the mean score would be if the entire population of fourth graders in the district enrolled in the program. And their best estimate, their best point estimate here, is that they're going to estimate that the mean score would be about 67.3. That's assuming this is a good representative sample. Now let's look at the margin of error. It is very unlikely that the sample mean of 67.3 really is exactly what the population mean is for all the fourth graders. You know, the chances of being perfect, I mean, we'd have to have a perfectly representative sample, and that's a very small chance. Now, hopefully it's close. You know, if we took a good sample, it shouldn't be very far away, but probably not perfect. So therefore, in order for this estimate to be useful, we need to know how close it is to that, how likely it is to be close to that. So if we think it could be off as much as 10 points, so if we're pretty sure that the real population mean is within 10 points of that, well, then we would estimate an interval of 67.3 minus 10 to 67.3 plus 10. So 67.3 minus 10 is 57.3. 67.3 plus 10 is 77.3. So we would say if we feel that the population mean is within 10 of that sample mean, we would say, hey, we think that the population mean is between 57.3 and 77.3, plus or minus. That is called the margin of error, is that plus or minus 10. So we're giving ourselves a 10, plus or minus 10 margin of error. Now, we just pulled that plus or minus 10 out of thin air here. We think that's acceptable, but we have no statistical backing for that being an acceptable value. So we really have no reason to pick the 10 out. The 10 has no validity there. It's just a guess. So we need to determine how large that margin of error really should be based on our data. So we do this with that sampling distribution that we reviewed here just a minute ago. When the sample size is large, remember we said if the sample size is more than 30, the central limit theorem applies. It tells us that in the distribution that the mean of the sample means is going to equal the population mean. And the standard error, in other words, the standard deviation of those sample means is equal to the population standard deviation divided by the square root of n, as we mentioned earlier. So recall for the example about teaching reading, the sample size is 100, the population standard deviation was 15, therefore the standard deviation of the sample means, or the standard error, is that standard deviation of the population, 15, over the square root of 100. Well, the square root of 100 is 10, so 15 over 10 is 1.5. So the standard error of the sample means should be 1.5. So what that's saying is if you did that bell curve, assuming the sample mean really is 67.3, the sample mean is close to the population mean, we're going to use that 67.3 as the estimate. One standard error would be 1.5 out, so that'd be, what, 65.8, and then this would be 63.3, subtracting 1.5. That's our standard deviation, each step out, going 3 steps out in both directions. And we know, of course, 68%, 95%, and so on from our empirical rule. We're going to look at that in terms of more exact with normal probabilities in a minute. So every confidence interval must have a confidence level. Now the confidence level is not a probability. It is a percent, so it looks a lot like a probability, but it's how confident we are, how assured we are. It's not what's the probability that this is correct. 95% of the time it should be correct if it's constructed well, but it's not a probability. The confidence level is a percentage between 0 and 100. Obviously, we want to be relatively confident, so very seldom do you see a confidence level between below 80. And most of the time, it's either 90% or 95%. Occasionally, you see like a 98% or 99% if it's something really important. So decide here, suppose we decide to construct a 95% confidence interval. What that means is we need to find, and we did this when we did our normal probabilities, the area on the curve that's bounded, 95% of the area is bounded by these limits. And of course, if it's 95% is within that area, 5% is outside, and that 5% is split half and half. So 2.5% here, that's where the 0.025 is, that's the decimal of 2.5%, and 2.5% up here, which is 100 minus 2.5 will be 97.5 there. So that is where the 0.025 there is, it should be actually 0.975 will be the area there, or the cutoff there. So that's the 0.975 probability there. If you're doing an inverse normal of 0.975, would give you the positive 1.96 here. And do an inverse normal of the 0.025 is going to give you the negative 1.96 here. Those are the z-scores. That is called the critical value. So for a 95% confidence level, we're taking 95% out of the middle of that normal curve. We get these z-scores here that form the boundaries of that 95% region, and those are our critical values. So 1.96, it's positive 1.96 and negative 1.96, but we just use the positive. The 1.96 is our critical value. So then our margin of error is found by taking the critical value times the standard error. So 1.96, remember that's a z-score. That's 1.96 standard deviations away from the mean. So now, since we're talking about a sampling distribution, we use the standard error is the standard deviation of that sampling distribution. So we have 1.96 times our standard error of 1.5 gives us a margin of error of 2.94. So remember before we just said plus or minus 10. What we're just finding out here is realistically, if we took that 67.3 or whatever that number was, we didn't have to go plus or minus 10. All we have to do is go plus or minus 2.94. And that's going to include 95% of all possibilities. So we're saying that would make 95% of the time that would include the real population mean. So this is what all they're showing here is, okay, so now we have that 67.3. We're going to subtract the 2.94 to get a lower limit of 64.36. And then take the 67.3, which is our sample mean, add that margin of error of 2.94 to get an upper limit of 70.24. So we are finding here, now we can say that we are 95% confident. 95% of these confidence intervals would include the real population mean. So 95% confident that the real population mean for those students would be between 64.36 and 70.24. So we had the point estimate. That was the terminology. We just took the sample mean, and we said, hey, we know that we figure the population mean is close to that. The confidence interval was then that interval where we said, hey, between this number and this number. Confidence level is that percentage from 0 to 100 that measures how confident we are that is correct. It's the success rate. That if we construct these intervals, 95% of the time that interval will contain the true population mean. And then that margin of error we found was how far we had to go above and below that point estimate to create that confidence interval. And that was found by multiplying that critical value we found from the normal curve by the standard error of the means, that standard deviation of those sample means. So now our second objective is to find the critical values for confidence intervals. So let's look at finding different critical values. So we've got that curve that is 100%, 100% or 1 probability. And if we want to find the critical value, alpha is the terminology used, is the symbol used for the critical value. It's like alpha of 0.10. That corresponds to a 90% confidence interval. 90% confidence interval means there's 10% outside. Alpha is the percentage outside of our confidence interval. So 1 minus alpha would be the confidence level. 1 minus 0.10 would be 0.90. That's 90% for the confidence level. So the critical value is always alpha, z of alpha over 2. So in a 90% interval, alpha is 0.1. Half of that is going to be 0.05. Well, 0.05, because that gets split each way. The 0.1 is the probability of being outside the interval. So that's 0.05 on the lower end and 0.05 on the upper end. So this boundary here is at the z-score that corresponds to the probability of 0.05. This would be, of course, 0.05 up here would be 0.95. But we just need to find one of them. And we know that they're going to balance out. So we already found for a 95% confidence level, that is 1.96 is the critical value. For 90%, if you did an inverse, let me pull this up here. Let's do second distribution, inverse normal of 0.05. This would be for 90%. It's going to give us 1.645 if we round it to 3 decimal places. 80%, if you think about that, 80%, that's going to be 20% outside, which is going to be split 10% and 10%, right? So we're going to look up the 10%. So that is second distribution, inverse normal, we're going to put 0.1, and that gives us negative 1.282 if we round it. So it'd be 1.282 would be our critical value, which is what our table shows. So you can see those values being calculated using that normal curve. So we find the critical value. Well, here they're just going to do an example. Finding the critical value for z sub alpha over 2 for a 92% confidence interval. So again, we're looking at 92% is in the middle of the curve. 92% is in. That means alpha is 0.08. So that means 8% is outside. So that's going to be 4% on each end. That 8% that's outside the interval gets split up to each end. So on this end, we're looking at 0.04. So we'll do our inverse normal of 0.04. Oops, let me clear that out. I'll try that again. Second distribution, 3.04. So inverse normal 0.04. That's going to give us negative 1.751 if we round it. which is what they pulled up here. Now I use the 0.04. They're using 1 minus the 0.04, and I'll show you that in just a second. I get negative 1.751. They're getting a positive 1.751 here. But remember, the critical level is, or critical value is always positive. What they did was they found this one here, which is 1 minus the 0.04, which is 0.96, gives us the same value. Got to remember here to get my inverse normal, then 0.96. So it's a positive 1.751. To me, it's easiest to use this one and then know that the negative, I'm going to get a negative result, and the critical value is the positive of that number. Okay, so we have a simple random sample. So in order for this confidence interval to work, we must have a simple random sample. If the sample we've taken is not a simple random sample, its information cannot be used to construct a confidence interval, because the information could be skewed if it was any other process. And the sample must be relatively large. If the sample is greater than 30, sample size is greater than 30, then this will always work. If the sample size is less than 30, so what if n is less than 30? Well, that's where, or the population is approximately normal. If the population is approximately normally distributed, we can get away with using a sample size of less than 30. Okay, so constructing the confidence interval when the population standard deviation is known. This is very important. We know what the population standard deviation is. That population standard deviation allows us then to find that margin of error. We need that to figure out how wide that margin of error has to be, because that allows us to calculate the standard error of the means. So we find the point estimate. So that's just taking the sample and finding the mean of the sample. We find the critical value. That's, again, from the curve. You take the confidence level, you put it in the middle. Then the percentage that's not within the confidence level has to be split to both sides. That gives you those boundary probabilities that you find the critical values from. Then find the standard error, which is the population standard deviation divided by the square root of sample size. That can be used to find your margin of error for the confidence interval. Once we have the margin of error, then it's our point estimate plus or minus that margin of error. So the lower limit of our confidence interval is the point estimate, in other words, the sample mean, minus our margin of error gives us the lower limit. Then our sample mean plus that margin of error gives us the upper limit. So to interpret that result, of course, whatever the level of confidence is, we are this % confident that the true population mean is within this range, within this interval. So let's do an example here. A machine that fills cereal boxes is supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes. Now, the sample size is small here. N equals 6 is found to contain a mean, so sample mean of 20.25 ounces. It is known from past experience that the fill weights are normally distributed. There's what we needed. Since the sample size is small, it's less than 30, we have to know that the population is normally distributed. If we're not given that information that the population is normally distributed, we can't proceed with a small sample size like that. If it's not normally distributed, or if we're not told it's normally distributed, the sample must be 30 or more than 30. So since it's normally distributed, the sample size of 6 is okay, n equals 6. And a standard deviation of 0.2. So sigma, our population standard deviation, is 0.2 ounces. So we're going to construct the 90% confidence interval. So the first step, we found our point estimate. That is the 20.25 from our sample mean. So we found that point estimate right there. The second step is to find the critical value. This is a 90% interval, we said. Find the 90% interval. So that means 90% is going to be inside this, which means there's 10% outside, split half and half to upper and lower. So that makes 5% here and 5% here. So this will be 0.05 is what that probability of that cutoff is. So on the calculator, I'm just going to do second. Distributions, inverse normal, 0.05. And I get negative 1.645. So 1.645 is my critical value. Standard error, we take the population standard deviation of 0.02, and we divide by the square root of the sample size. So divide by the square root of 6. We get a standard error of 0.08165. Now, at this point, I always get questions of, how do we know where to round that off? Great question. We aren't really told. Always round at least one digit past what you want to express the answer in. Usually you'll go a couple digits past. Now here, this one's expressing the answer to 4 decimal places. A lot of times I only express it to 3. Usually I would say express your answer to at least 3 decimal places, and therefore do all your calculations to 4 or 5, and round off your final answer to 3. Here they're going to 4. So hopefully the problem will specify rounding for you. And in Connect Math, I know they do specify rounding for you. So we multiply the standard error by the critical value to obtain the margin of error. So we had the critical value is 1.645. That was this. The standard error, that's this. Multiply those together and we get a margin of error of 0.1343. So that means this is going to be plus or minus 0.1343 from our point estimate. So there we go. Our point estimate of 20.25 minus the margin of error gives us our lower limit, 20.12. The point estimate of 20.25 plus our margin of error gives us an upper limit of 20.38. So here's the big one, the interpretation. A lot of people word this wrong. A lot of people say, well, 90% of all intervals contain this. No. The interpretation, the proper interpretation is we are 90% confident the mean weight mu of the population is between 20.12 and 20.38. If we were to draw many, many different samples using this method to construct the corresponding confidence intervals, then in the long run, 90% of them would include the true population mean. So that 90% confidence means if we construct many, many, many of these confidence intervals based on different samples, 90% of them will contain the true population mean. 90% of them should contain the true population mean if we've done everything correctly. So the z-interval command in the calculator, when we do that z-interval command, there's 2 different possibilities. So I do second, not second, sorry. Hit stat and go to test. You see z-interval is option number 7 down there. So we select z-interval. And our input can either be data or stats. To select data as your input, you have to go to the lists first. So you'd have to do, let's get out of here, exit out of here. You would actually go to stat, edit, edit. That'd take you to your list. And you would have to enter all the data in one of these lists. So you'd enter all the data in list 1, and then you'd use data in as your input. If you don't have all the data put into that list, then you go to stats. Let's say you know the mean of the sample and stuff like that. Then you'd use stats. So for that last one we did, we know that the population standard deviation was 0.2. The sample mean was 20.25. Don't know why I blacked out on sample mean there for a second. N is our sample size. That was just 6. And our confidence level is 90, so 0.9 goes in there. We hit calculate, and it will pop up. That's our interval that we just calculated. Notice the calculator generally only goes to 3 decimal places, 20.116 to 20.384. So again, this is outlining that process that I just showed you. And you can see they get the same output here that I just did, getting that interval. Describe the relationship between the confidence level and the margin of error. Well, this one should be relatively obvious. The more confident you want to be, the larger your interval has to be. If it makes sense. If here's your point estimate and here's your interval, that's a small interval. Chances that catching the population mean are smaller. If I want to be more sure, more confident, I would make a wider interval. So that has a better chance. It's more likely, I gotta be careful, more likely is bad. I'm more confident now with that wider interval that I have captured the true population mean within that interval. So 70% confidence level is going to have a pretty small margin of error because you only have to be right 70% of the time. It only has to be wide enough to catch that true population mean 70% of the time. The 95% interval is going to be a medium. That's usually what's used for most purposes. It's the most reliable. It's reasonable. It's fairly reliable. Only 5% chance that it's going to miss. It's fairly reliable, but it's also practical. 99.7, well, that's going to be a much, much wider interval because we need to catch that true population mean 99.7% of the time. The problem is it's a huge interval and it doesn't narrow things down enough for us to be able to catch it. What this graphic is below here, what each of those lines are, you can see that's a line there. That's actually an interval. This end of the line is the lower limit. This end of the line is the upper limit. And you can see down through here, this interval, barely catches the big line going vertically is the value of the population mean. This interval here barely catches the end of it, barely catches that population mean. This interval over here misses it completely. If you were to go up through here, this is a 70% confidence level. So we constructed each of these is a 70% confidence interval. If you were to go up through there, 70% of those actually contain the population mean, which means 30% of them don't. So you can see that one's not very reliable. 30%, that's almost 1/3 of the time it misses the true population mean. It does not include that true population mean. 95%, well here, 19 out of 20 times it hit that true population mean. So I don't know how many are in this. It looks like about 50 or so. Looks like they only missed, 4 or 5 times going up through there. That's not bad. Actually, not even. It looks like they only missed about 2 or 3 times going up through there. I see one here that missed, and I see one here that missed. And it looks like all the others caught it. So that's pretty reliable. Here, I don't see any that missed there, but you can see they're much wider. These intervals are that wide compared to these intervals being that wide. It's much more useful to have it narrowed down further. Even if you are going to miss 1 or 2, it's nice to have that narrowed down to a much smaller range to work with. Find the sample size. Here's the tough one. This one, want to make sure you've got this down so you can do this. I mean, you can use the calculator to help you, but the calculator does not have a built-in function for this. So what we're looking at here is we're limiting our margin of error. We want to be within a certain distance of the true population mean. And to do that, we limit our margin of error. So can we make the margin of error small? The way we make our margin of error smaller, there's 2 ways we can do it. We can reduce our level of confidence. So we go from 95 to 90 makes it smaller. As we saw in that graphic up there, the 70% intervals were really small, but not as reliable. Or we can increase the sample size because the standard error of the means is the population standard deviation divided by the sample size, the square root of the sample size. The bigger that sample size is, the smaller that standard error is. The smaller that standard error is, well, when we multiply it by the critical value, we're going to get a smaller margin of error. So we can increase the sample size to get a smaller margin of error. So if we have a certain margin of error that we desire, what we can do is we can take this formula here and we can solve it for n. So multiply by the square root of n on both sides, divide by z sub alpha, and then square it, get rid of the square root. What we end up with, or not divide by z sub alpha, sorry. We square it to get rid of the square root and divide by m as the margin of error. So what we get right down here is that formula once we've solved it. N is equal to, it's still z sub alpha times our population standard deviation, dividing by that desired margin of error, and then of course because n was square rooted up here, we have n squared here. So it's squared here to get rid of the square root. So how do we apply that formula? Let's look at an example. Scientists want to estimate the mean weight of mice after they have been fed a special diet from previous studies. It is known that the weight is normally distributed. So normally distributed means we don't have to worry about our sample size. And the standard deviation is 3. So we know the population standard deviation, 3 grams. How many mice must be weighed so that the 95% confidence interval will have a margin of error of 0.5 grams? Now it should say 0.5 grams or less. So to try to get that margin of error to 0.5 grams or less, we're using our formula here. N equals z alpha over 2. In other words, the critical value is all that is, times the population standard deviation divided by the margin of error and then squared. So it's 95% confidence interval, so our critical value is 1.96. Population standard deviation was 3. And we wanted to be within 0.5 grams, so that's our margin of error. So we do 1.96 on the calculator. I'm going to do 1.96 times 3 divided by 0.5. Now I'm going to hit equals. Then I have to square that. So x squared. And I get 138 they're rounding up to 138.30. When we do this sample size, we always round up. Even though that was 138.3, we go up to 139. Because if we round it down, that sample size is going to be too small. The margin of error is not going to be less than 0.5. So we'd rather have the sample a little bit too big than have it a little bit too small. So we always round up. Distinguish between confidence and probability. So here's the one that a little tricky and a lot of people confuse. So a cereal box example, 90%, we had a 90% confidence interval. So what it's tempting to say that 90% of the time, or the probability is 90%, that the true mean is between that. That's not true. It's not 90% probability. It is, what we would say is, you know, the term probability means a random event. And since you've already calculated this, it's not random anymore. There are absolute numbers out there. So the real meaning of that 90% confidence is if we did a bunch of samples and constructed these 90% intervals, 90% of these intervals would contain the true population mean. So in other words, we're 90% confident that the population mean is within this interval. So if we're looking at the method used to construct it, the method will succeed in covering the population mean and including the population mean 90% of the time and fail 10%. So therefore, it is correct to say the method for constructing the interval itself is not 90% probability, but the method used for constructing the interval has a 90% probability of accurately including the population mean. So the method has a 90% probability. The interval itself either includes it or it does not. It's no longer random once we've constructed the interval. Okay, so the review of the things we learned what the interval was and how to construct it. Once if we knew the standard deviation of the population, we learned how to find the critical values. We found the margin of error and how that was affected by the sample size and critical values. And we learned how to find that sample size required to get a desired small enough margin of error. Okay, with that, I'm going to pause for a second while I pull up the next section here. So in this section, we're looking at constructing those confidence intervals again, but what if the standard deviation of the population is not known? So now, when we do this, we're going to be looking at a different distribution. We cannot use that normal distribution, the Z distribution anymore. There is a distribution called the student T distribution, or often just called the T distribution, and it's actually several distributions that depend on the sample size for finding those critical values now. That tells us how many standard deviations we have to go away from the mean or the point estimate in order to construct our interval. So let's look at the student t distribution. The student t distribution. You know, we've seen the normal distribution stuff. The t distribution works the same way. It's a normal curve, but it's slightly narrower or wider depending on the sample size, where the normal curve doesn't matter what the sample size is. But if we don't know the value of the population standard deviation, we can replace it with the sample standard deviation. So that's the key here. We don't know the population standard deviation. So we're going to replace it with the sample standard deviation. However, the critical value is calculated off of the z distribution. We can't do that because this quantity does not have a normal distribution anymore if we don't know for sure what that, if we're using the sample standard deviation instead of the population standard deviation, this may not be normally distributed anymore. So this distribution, this value, the z-scores are now going to be distributed according to that t distribution, or student t distribution. So the student's t distribution is more spread out than the normal curve. What that means is we're going to take a wider margin of error just to be more sure, because we not totally confident how close our sample standard deviation is to the population standard deviation. So we take a wider margin of error to take a wider interval with the same level of confidence. These intervals will be wider than they would if we knew the population standard deviation. And so we also have to then know the sample size, and to know this, the sample size is used to determine something called the degrees of freedom. The degrees of freedom is just the sample size minus 1. Like I said, the t distribution is different depending on the sample size, depending on the degree. Technically, it's the degrees of freedom that change the t distribution. So let's get a picture of the t distribution here. You can see with 1 degree of freedom, I mean, all these look like bell curves, but with 1 degree of freedom, it's more spread out. You can see it's wider out here. Let me highlight that one for you. This here is 1 degree of freedom right here. It's more spread out, lower at the peak and higher out at the sides out here. If we get up to 10 degrees of freedom, which is in the red there, that's just in the red here, you can see it's getting really close to the normal distribution. It's a little bit lower in the middle than the normal distribution and higher outside here. The red's higher than that solid black line. But it's getting really close to it. So the more degrees of freedom we get, the closer this is to the normal distribution. And that's why we use that. We had mentioned the sample size being 30 or more, or larger than 30. When the degrees of freedom reach 30, the student t distribution is almost identical to the normal distribution. So to find the critical value, we're going to do the exact same thing. We take whatever our confidence level is, that would be the percentage in the middle here, and we split up the percentage to each side. So it's going to be an alpha over 2 on each side again. But now we have to look at corresponding rows in a table that tell us what that probability is. So in the t distribution table, let's say our sample size here, do they give a sample size? No, they don't. Here they're going to give us a sample size. So let's say our sample size is 10. If n equals 10, that means our degrees of freedom, DOF is the abbreviation for degrees of freedom, is 9. Remember, it's the sample size minus 1. This is a 95% interval, which means alpha is 0.05. So alpha over 2 is 0.025. So we're going to look up either 0.025 or 1 minus that would be the 0.975. Those are our two endpoints for the probabilities. Those are boundaries. So let's look up what that comes up to. Now this isn't showing the top up here. Up top here, this would have to say 0.025. 9 degrees of freedom, 2.262 is our critical value. Now compare that to, remember we did second distribution, inverse normal, 0.025, gave us 1.960 for the z distribution. So you can see 2.262 is quite a bit larger. I mean, that is almost 3/10. It is 3/10, a full 3/10 larger. So it's going to give us a much wider interval. So we've got if the desired number of degrees of freedom isn't in the table, if the desired number is less than 200, use the next smaller number in the table. If it's greater than 200, just go to the z-distribution. Now we can use the calculator for finding it. I believe this calculator has the inverse t. It does have inverse t as option 4 there. Now for the inverse t, we have to put in the value, so 0.025, and I have to put in the degrees of freedom, which is 9. I believe that's right. I don't know. I don't think I have to put the degrees of freedom in first. Hopefully that comes out. And there it is, negative 2.262. So we had a 2.62 was our critical value that we had here. So we get the same. So anyway, I don't use that table hardly at all because the table only has certain values on it, and you get up to larger sample sizes, you're finding your degrees of freedom most likely won't be on the table anyway. So I always use the calculator for that. We have a simple random sample. So these are assumptions made. Again, just like with the other one, we still have to assume if we did not take a simple random sample, this won't work. And the sample size is either large again, 30 or more, or the population is approximately normal. So again, if we have a sample size less than 30, we have to know that the population is approximately normal. Okay, construct the confidence interval. So let's go ahead and do it. So this is our process again. Everything is the same other than we find our critical value from that t-distribution. Otherwise, the rest of the process is the same. You find the critical value, you find the standard error, compute the margin of error from that, and you find your interval. So let's go straight to an example rather than just reading through that process. So here we have a sample of 123. So n equals 123. People at age 18 to 22 reported number of hours they spent on the internet each week. The sample mean was 8.2. So the sample mean, that's our point estimate of 8.2 hours. With the sample standard deviation. That's a sample standard deviation. So that's not a sigma, that is an S of 9.84 hours. Now it doesn't say, we don't know the population standard deviation, but they're giving the sample standard deviation and they're not giving a population standard deviation. So we know that means that we are going to fall into a t-distribution. So we want the 95% interval, so alpha equals 0.05, 100 minus 95 is 5%. So then we're going to do alpha over 2 is 0.025. And we just found that on the calculator here, but we need to do a different number of degrees of freedom here because that was 9 degrees of freedom. We need now how many degrees of freedom? 123 minus 1 is 122. Now this example, they're probably going to use the table, so they're going to get a slightly different critical value. But I'm going to calculate on the calculator here. Second distribution, inverse t, 0.025, or I could have done 0.975 would have been the upper end, it would give me the positive value, comma, 122 degrees of freedom. That's the 123 minus 1. Now I get negative 1.979, so it'll be 1.980 is my critical value from the calculator. Now if they're using the tables, they might have to round for degrees of freedom because that 122 most likely will not be on our table. So their critical value, they got 1.94 because, let's see, yeah, they had to go down to 100 degrees of freedom because 122 wasn't on it. Their table skips from 100 to 150, I believe. So they had to round down to 100. So they got a larger interval. We got 1.98. They've got 1.984. So playing on the safe side, going to the smaller degrees of freedom is going to give you a larger critical value. So you're going to get you're playing your confidence interval on the safe side. You're making a larger interval, so you're being safer. So now to know the margin of error is going to be that critical value. Again, we had 1.980 we found as the exact critical value. The standard error of the means we're taking the 9.84, which is our sample standard deviation. Remember, that's from the sample, divided by the square root of our sample size. So this is not truly the standard error of the means. It's an approximation of the standard error of the means. We get a margin of error of 1.7603. So our sample, or our interval, is going to be plus or minus 1.7603 away from our point estimate. And our point estimate, remember, was 8.2. That was our sample mean. So if we take 8.2 minus the 1.7603, just 1.76, we get 6.44. Take the 8.2 plus the 1.76, we get 9.96. So our interval is, this was 95%, so we are 95% confident that the mean number of hours for the population is between 6.44 and 9.96. So then we got the t-interval command on the calculator that's very helpful. And let me just punch this in. So we're going to stats, tests, t-interval, we're going to have to arrow down a ways. Notice after the z-interval is t-interval is option 8. Again, we're doing stats. Data, we'd have to have the list of raw data points in the list. X bar here, that's our sample or standard or sample mean, which is 8.2. SX, since we don't have the population standard deviation, we're going to put in the sample standard deviation, 9.84. N is the sample size of 123. Our confidence level now is 0.95. We hit calculate, and it spits out our interval. 6.44, again, they went to a few more decimal places, but 6.44 to 9.96, which is what we had when we did it by hand. So, of course, they're just showing that being finished off here, getting that same result we did down there. So we've learned a little bit about the student t-distribution, and we've looked at constructing that confidence interval for the population mean. Remember, even though we're using the sample mean, what we're doing here is we're using the sample mean to estimate the population mean. So a lot of people get confused here. You know, it's saying construct the confidence interval for the population mean. A lot of people, we don't have the population mean, we don't have the sample mean. And that's the point. We're using the sample mean to estimate the population mean. So we're using that sample mean to construct a confidence interval to estimate the population mean. So the interval really is trying to describe the population mean. Okay, that is it for section 2. So I'm going to pause here for a minute to pull up section. Okay, so in section 3 here, we're going to look at confidence intervals for the population proportion. This is actually a little bit simpler than the others. So we're going to construct the interval. We're going to find the necessary sample sizes. You'll notice when we were looking at that last section where we did not know the population standard deviation, we didn't do a sample size calculation, because if we don't know that population standard deviation, we needed that population standard deviation in that sample size formula. So if we don't have it, we can't do that sample size estimate. For a population proportion, since when we're dealing with proportions, think of like the binomial distribution. The standard deviation is actually found from the proportion itself. So if we're looking at a proportion, we always know the standard deviation. So we're going to be able to do a sample size calculation here. Now we're going to describe this confidence intervals with small samples. So construct a confidence interval for a population proportion. So here in the music organization, Little Kids Rock surveys 517 music teachers. So N equals 517. And 403 of them said that video games like Guitar Hero and Rock Band, in which 442 players try to play music in time with the video image, have a positive effect on music education. So 403 of them. So what we define here is X is going to be 403. Again, think of this similar to the binomial distribution. N is 517. That's our sample size. X of 403, that's how many are in favor of this. So that's our number of successes out of the 517 trials. assuming these teachers to be a random sample. So again, we have to assume that it's a simple random sample. We would like to construct the confidence interval for the population proportion now. So our steps. We can find the point estimate. The point estimate for the population proportion is going to be the sample proportion. So we're going to take that x, remember x was 403, over n. So we got 403 over the 517. That's going to give us that point estimate of the population proportion. We're going to calculate this on the next slide, but we'll do it here right now just to show you how to do it. So 0.7795 is where we'd probably round that off. The number of individuals in the sample or in a specific category, that's x. That was our 403 that said they were in favor of it. N is the sample size. That was the 517. P is that proportion that we get after we divide. So right there, x over n. They use p hat because p is the population proportion. P hat is the sample proportion. That's what the little hat means. It's from the sample, not from the population. So once we've found that, then our standard error, the standard deviation is just, remember for binomial, the standard deviation is just the square root of n times p times 1 minus p. Well, to divide that by the square root of the sample size, we end up getting a standard error here of just p times 1 minus p divided by n. So our margin of error, we find our critical value. Notice this is back to a z-score. For proportions, we always use the normal distribution. So it's always z distribution times our standard error again. So that's our margin of error. Our interval is just going to be our point estimate plus or minus our margin of error once we have it. So then let's take a look here. Things that we must have to use a confidence interval for proportion. Just like before, we must have a simple random sample. So to do a confidence interval, we must have a simple random sample, period. Here's an extra qualification that wasn't out there for population means. The population must be at least 20 times the sample size. So if there's 100 members of the population and we take a sample of 10, not only is that a small sample, but that's only, the population is only 10 times the sample size. We cannot do a confidence interval then. The items in the population are divided into two categories. Well, they're either in the category that we want or they're not. So yes, they're either in or out. So that's kind of like the binomial, just like the binomial conditions there. The sample must contain at least 10 individuals in each category. So yes, the sample must be large enough to contain at least 10 individuals in each category. What that means is, let's say that 95% of the population is in one category and only 5% is in the other. Well, I have to take a sample large enough that there's at least 10 people in this smaller category. So if I have those estimates, I can use I have to have at least, if it's 5%, I have to have at least 200 in my sample to guarantee that I'm going to have at least 10 people in that category. Now, again, we don't know that proportion, so having estimates is helpful. So the process, find the point estimate of P, just like before, we find the point estimate. Find the critical value, again, just like our other options. Find the standard error, again, just like that's always step 3. It looks a little different now because we're using the standard error for a proportion is a little different than the standard error for a mean. And then we find our critical value, and our margin of error is from that critical value and the standard error. So then the point estimate plus or minus the margin of error gives us our lower limit. Point estimate plus our margin of error gives us our upper limit. So same process again. I know I breezed through that really quickly, but the example here is going to be more meaningful to us than the generic process. So here, 517 music teachers, 403 said that the video games were good for the students, had a positive effect on music education. We're going to construct the 95% confidence interval. So again, N is 517, X is 403. 95% confident means alpha It's 0.05. Looking at a z-score, so if we're looking at that curve, that 0.05 is split to the side, so this is going to be 0.025 again. It's going to be 0.975. If we did it on the calculator, the inverse z, I'll do it again, inverse normal, we get negative 1.960. So this is 1.960 is our critical value. Now they also notice 114 who do not. That's double checking. N minus X is more than 10, so there's at least 10 that are not in our desired category. We had to make that double check. I forgot to do that there. The population of all music teachers in the U.S., we have a sample of 517. 20 times that would be 10,000. A little more than 10,000. So we have to make the assumption there's at least 10,000 music teachers in the U.S. If not, this would be hard to do, or we wouldn't be able to do this interval. I think it's pretty safe to say that there's at least 10,000 music teachers in the United States. Okay, so then go ahead and compute. We found the point estimate. We found that before. The 403 divided by 517. Our confidence level, or critical value, is the 1.96 that we found ourselves earlier. So the margin of error is the 1.96 times the standard error. Now, since we don't have the population proportion, we have to use our sample proportion in here. So that's why we went out to 6 decimal places there. So it's P, which is our sample proportion, times 1 minus P, then divided by that sample size, then square rooted. So we get a margin of error of 0.0357. Now I'm going to enter this in the calculator just because this can be tricky to enter in. So it's 1.96 times second square root. And entering this it's just straightforward. 0.779497 times parentheses 1 minus 0.779497 close parentheses divided by 517. It's right in there. Hit equals, and there it is, 0.035738 if we round it. So that means our interval is our point estimate minus the margin of error, which would be 0.744 rounded, to our point estimate plus the margin of error, which is 0.815 rounded. So our interval, we're 95% interval, so we're 95% confident that the true population proportion is between 0.744 and 0.815. So that's our interpretation, 95% confidence between those values. Suppose that the video game manufacturer claimed that 80% of music teachers believe that Guitar Hero and Rock Band have a positive effect. Does this confidence interval support or contradict that claim? Well, the confidence interval isn't necessarily able to support a claim, but it can contradict it. If 80% is not in the interval, then the interval would contradict it. Well, 80%, of course, is 0.8. And the interval goes from 0.744 to 0.815. So 0.8 is in the interval. So this interval does not contradict that claim of 80%. According to this interval, 80% is a very, very possible result, true result. Now, that doesn't support the 80% because, remember, there's a chance that the true population mean is outside this interval. So we can't say it supports it, but it does not contradict it. So on the calculator, let's enter this information. So we're going to go to stats again, tests. I go down to Z interval. So there's one proportion Z interval. It's option A. One prop Z int. That's one proportion Z interval is what that stands for. X was 403. N was 517. Confidence level is 95%, so 0.95, and calculate. And there it spits out exactly what we had there when we did it by hand. There you can see their output right there. Exactly what our output is here on the calculator. Okay, so let's find the sample size necessary to get our margin of error down to a certain size. So again, our margin of error is this formula here. We're going to solve it for n right here. So we're going to have to square everything to get rid of the square root and then move the n around. And what we get is this right here. The sample size is equal to the sample proportion, or the estimate of the proportion. We haven't taken a sample yet, so we don't know what the sample proportion is, so we have to have an estimate of that proportion. And we're going to talk about this here in just a minute, that estimate. If we don't have an estimate, then we've got to figure out what are we going to use there. Times our critical value divided by our desired margin of error. That part's going to square. So let's look at that here. We need to either have an estimate for that p. So use a value that's from a previously drawn sample. That's possible. Or if we don't have any sort of estimate for p hat, we use 0.5. 0.5 is the one that makes the margin of error the largest. And if we don't have any previous knowledge of p, the safest bet is to make the confidence interval as large as possible. So that'd be the largest margin of error. So by using 0.5, we're maximizing this so that we can make we'd have to get a larger sample. And again, it's better to have too large of a sample than not large of enough sample. So it's kind of like a worst case scenario type deal. So let's do an estimate here. So in this estimate, again, we've got the 517, 403 said that it's a positive effect. If at the 95% confidence level, if we want to get the margin of error down below 0.03, what would be the necessary sample size? Well, we use that estimate from the previous sample, 0.779497 times 1.779497 times our critical value of 1.96. That's from the 95% confidence is the 1.96. Our desired margin of error, we said we wanted to stay at or below 0.03. So then I'll show you how to punch this in. So 0.779497 times parentheses 1 minus 0.779497 close parentheses times parentheses again 1.96 divided by 0.03. When I close those parentheses, oops, I don't know why that didn't register there. Divided by 0.03 squared, it equals, we get 733.666, 733.67 rounded. Again, we always round up. So this would have rounded up anyway, but we always round up. So 734. Like we said, better to have too large of a sample than not large enough. If we change the number, if we didn't have that estimate from the previous sample, we would have had to use 0.5 for p hat. So that means 0.5 times 1 minus 0.5 would be 0.25. So that's why they use that there. That would give us a much larger required sample. So here, this is saying 734 is large enough. Here it's saying 1,068 is required. So having that estimate of p hat allows us to narrow down that sample size a little bit smaller. If we're looking at expenses here, it'd save us money by taking a smaller sample. But again, if we don't have that estimate, we can always use p hat of 0.5. That'll give us a much larger sample, but it plays it on the safe side. Describe the method for constructing the confidence interval for small samples. So we don't really use this much, but we would adjust the sample proportion by taking x plus 2 over n plus 4. So that gives us an adjusted sample proportion. That's p tilde. In this class, we're not really going to use that. The calculator will automatically adjust for that, by the way. But for this class, if it's a small sample size, we're just not going to deal with it. That's saying is that there's not at least 10 individuals in each side in each side of the category in our sample. So like I said, we're not going to deal with that in this course. So I'm going to leave that off of this. So I'm going to pause here for a second while I go to the last section of this chapter. Okay, so the last section here, this is really a short one. How do we know which method to use? We've looked at 3 methods here so far. We've got the first method is sigma is known. In other words, the population standard deviation is known. The third method is sigma is not known. The fourth method, or the third method is a proportion. Well, it should be pretty simple. If we're talking about a proportion, if we're asked for the confidence interval for the population proportion, obviously we're using the third one, the proportion. That's the section 3 there. We have the standard error is the square root of p times 1 minus p, and so on. So that one's usually fairly easy to spot. Both of these, however, are talking about confidence intervals for the population mean. And to tell the difference, we're either told sigma, we're either told the population standard deviation, or we're not. If we're not told the population standard deviation, we're usually going to be told a sample standard deviation. So let's go ahead and look at what they say. So determine them, which method to use when constructing a confidence interval. We're going to look at, first of all, is it a population mean or a population proportion? If it's a proportion, of course, we're using the 1 prop z interval. Next is the standard deviation of the population known right here. If yes, is the sample size greater than 30? We can use the z method. If no, is the population approximately normal? We can use the z method. If the sample size is smaller than 30 and the population is not approximately normal, it says consult a statistician. There's something called non-parametric methods that would be used. It's a little bit above the pay grade for this course. So yes, if the sample size is smaller than 30 and the population is not approximately normal, we're not going to tackle it in this course. If if the standard deviation of the population is not known, so if that's no, that we don't know it, same question. Is the sample size greater than 30? If it is, we use the t method. Is the population approximately normal? If it's not, the sample size is not greater than 30, well, is the population approximately normal? If yes, we still use the t method. If no, we can't do it. So basically, if the population is not approximately normal, and the sample size better be bigger than 30, or we can't do it, no matter what. The biggest thing is, if we know the standard deviation of the population, we're looking at the z method, if we can do it at the interval. If we don't know it, we're looking at the t method. Again, the only exception to those is if the sample size is less than 30 and the population is not normal, then we can't do it at all with our methods. So that's basically it. That is it for Chapter 9. If you guys have any questions, let me know. Otherwise, have a great week.